All right, so moving on from chapter 4, we now want to take on chapter 5 in our textbook. And the primary topic of chapter 5 is thermochemistry, right? Or this could also be referred to as thermodynamics. So the root here, thermo, means heat, right? So this is the heat associated with chemistry, or the heat associated with a change. So we're going to be looking at heat moving in and out of materials, but then we're also going to be looking at how heat can flow relating to a chemical reaction as well. So a few definitions here to get started. So thermodynamics, this is basically study of heat transfer or heat change. And that is pretty much what we're going to want to calculate. How does heat change temperature? How does a hot object affect a cold object it comes into connection with? To evaluate some of those issues, there's a couple things we want to think about here, kind of in general, because they'll pop up as we're evaluating certain problems that we're going to need to tackle. So we've talked about how matter is conserved over the course of a chemical reaction, right? We can balance an equation because we'll have the same mass on each side, reactant side, product side, and that translates to having the same number of each type of atom on each side of the equation. There's a similar law for conservation of energy. So one of the fundamental laws of physics is that energy isn't created or destroyed, right? But it can change form. So in terms of chemical systems, we'll often think about the fact that there's kinetic energy, which is energy associated with movement, right? And we can also directly associate that with temperature. But there's also there's also potential energy, which is stored energy. And in a chemical system, energy could be stored in the bonds that we have between atoms, right? So it's somewhat dependent on the structure of certain molecules, and of course that can change from reactants to products. But what we want to keep in mind is stored energy could be converted into kinetic energy. If we take some stored energy and turn it into kinetic energy, that might cause the temperature to go up. If we take some heat and then store it as potential energy, that could cause the temperature to go down. But those two quantities of energy are always going to be related to each other. If one goes up, the other is going to have to go down by that particular amount. Now, we can use that relationship as a way to think about how to solve problems. There's a very similar issue when we start to think about just the movement of heat. So not even necessarily a chemical reaction, but just a hot object coming into contact with colder objects. When we're looking at a problem, we may want to define a system that we're trying to evaluate, and then the surroundings would be everything around it. So this could be, for instance, if you take a hot piece of metal and you drop it into a reservoir of water, we might think of the hot object as the system that we're studying. What's its temperature? How hot is it? How much energy does it have? Right? And then the surroundings might be the water around it after we drop it into that water. And we need to make that distinction because heat is going to leave the hot object. So if the system is our hot object, heat's going to leave the hot object. Where's that heat going to go? It's going to go into the surroundings. That's a key piece of information we're going to need to evaluate our problem, because the heat that leaves the system is going to be equal to the heat that went into the surroundings. If the heat flow is reversed, then the heat that goes out of the surroundings is going to be equal to the heat that flows into the system. So you just want to be on the lookout for those terms when they come up with regard to problems. Okay, now heat and energy is something we have not talked about before, so we'll need some units to describe heat and energy. There are two kind of fairly common units here that are used for heat and energy. The calorie is basically an older unit. Was defined relative to water. So the calorie was defined as how much heat you'd have to add to 1 gram of water to raise its temperature by 1 degree Celsius. The SI unit, so the one we are primarily going to use, is called the joule. So a joule would be a measure of how much energy or how much heat we have in a particular situation. We may need to convert between these two. So the relationship between them, 1 calorie is equal to 4.184 joules. And we'll actually see this number 4.184 pop up a few other places as we're talking about this topic. Because, like I said, with calorie, it was defined as how much heat you need to raise 1 gram of water by 1 degree Celsius. That would mean this is how much heat you need to do that same thing. So this value, 4.184 joules, is going to be related to the way water absorbs heat. Calories, joules actually are fairly small amounts of heat. So it is pretty common to throw the prefix kilo in front here. So 1 kilojoule is equal to 1,000 joules, right? The same way we've seen kilo in the metric system. So that is something we would have to do fairly common. You might do that with calories too. A calorie, 1,000 calories would equal 1 kilocalorie. And you may have heard of calorie in terms of the energy associated with food. So how many calories are in the food you eat. That calorie is, from a scientific perspective, is a capital C calorie. So the dietary calorie is actually a kilocalorie in relationship to this definition of a calorie. So it's actually the amount of heat that would raise 1,000 grams of water by 1 degree Celsius. Okay, now we want to be able to relate all of this information, energy and movement of heat, etc. So there's one more kind of definitional thing we need here that we're going to be able to use to start doing some calculations. And this is called the specific heat capacity. Now, there's a lot of variation from textbook to textbook. Some places will call this the heat capacity. So I think it's really important that you keep track of the units that are being described. I've also seen books where this is abbreviated as C, right, for capacity, or SH for specific heat. They're all used interchangeably, right? So again, you should be aware of the fact that there's more than one way to abbreviate something. I learned this as SH, so that's how I will usually put it into an equation, but you're certainly capable of understanding when a textbook uses capital C with a subscript SH means the exact same thing. This is the energy transferred as heat that's required to raise the temperature of 1 gram of a substance by 1 degree C. Now in this case, since we're looking at temperature change, degrees C and Kelvin are exactly the same. So it's a lot easier to do this in degrees Celsius since that's the way our temperature measurements are usually done. You could change everything to Kelvin, but again, since it's a temperature change, you would get the exact same value for a Kelvin temperature change as a Celsius temperature change. Not the same if we're talking about what's the temperature reading, which is something we'll do in the next chapter where we're going to have Kelvin. So I mentioned for water, right, this is, so let me put SH there. So the specific heat capacity for water is 4.184 joules. That's the amount of heat per gram degree C, right? So it's how much heat is raising 1 gram of the material by 1 degree Celsius. This gives us an equation that we can use to relate all of the information that is related to specific heat capacity. So the specific heat capacity is going to be equal to, right, joules, that's how much heat is transferred, divided by grams, that's mass, and also divided by degrees C, and that is going to be the change in temperature. So I've got the triangle here, that's the Greek letter delta that symbolizes change. So the specific heat capacity would be equal to the heat transferred divided by the mass of the object and the change in temperature. Now, one other thing I should add here for the equation, heat is often abbreviated as Q. So you may see it written like this, Q over M. So lowercase m here I'm using as a stand-in for mass, and then the temperature change. So make sure you keep that in mind. It's how much the temperature changes, not what is the temperature, but how much it changes, because you'll have temperatures often in these problems, and if you just plug in that temperature, you're probably not going to have the correct answer. Okay, now we've got some examples of applying this equation, but we've hit about the length I want the video to be, so we'll stop there, and I'll pick up the sample problems in the next video.